different kinds of instruments of different vendors and different types. There's a standardized way for doing measurements and storing data, which makes it easier for people to collaborate and share data between group members. And finally, the software is mainly driven through a user interface, which simplifies adoption and makes it easier to set up and run experiments. And all these things together kind of combines to make it easier and faster to do quantum experiments. The company was founded back in 2015, was at that point headquartered in Sweden, and we've been working with Keysight since 2016. We're mainly selling the software for quantum applications. I think roughly 90% of our customers are doing some sort of quantum application, and Lab is being used in a large number of countries all over the world. The company was acquired by Keysight back in late 2019, and since then we've set up a specific Keysight lab or office in Cambridge, Massachusetts, so close to Boston, where MIT is. And that's also where I'm currently located. So in general, test and measurement software is used to control, automate, and perform experiments in the lab. So this is a pretty common task for a wide range of industries, going from device testing, calibration, characterization of devices, for example. And a general problem is that people who do these experiments tend to write not the best code. So you have the situation where you get to situations where you have code bases that are difficult to maintain or often not the most efficient. And 10 years ago, it was still possible to do it that way because you had few instruments and small applications with few instruments. But today, especially with quantum computing, you have a large increase in complexity with large number of measurement systems, large number of devices to sensors, and you need to have more flexible way to define and set up experiments to be able to fast and quickly reconfigure your application. And that is how we kind of come up with the idea of building a software that is more flexible, more simple to use, and more scalable, especially for quantum. So Labware consists of 3 different modules. It has an instrument server. Let me show this highlighter. On the left here, the instrument server talks to different instruments of different kinds, and this could be really any kind of instrument. It could be a DC source, it could be a Keysight NRBG or any other type of instrument. And then there is the measurement editor, which talks to the server to output and read values in these instruments. And finally, there's a log browser for looking at data that is stored after the measurement is complete. I will now go through these different components to show what it looks like in real life. So start with the instrument server. The instrument server, again, handles communication with instruments. We see here on the right is what it looks like when it's open on a computer. You have a lot of different instruments connected and what it can do essentially. And again, this can be talking to the computer with different interfaces, typically TCP/IP, but also supporting legacy interfaces like GPIB or serial. And one strength of this approach is that all these instruments run in separate processes, which means they can run independent of each other. The next part of the Labware stack is the measurement editor, which is where you kind of define and run experiments. And this window looks like this on your computer. You add a number of instruments you want to include in your measurement. It could be, again, different kinds of instruments. It could be DC sources or generators or anything pretty much. And then you select which of these quantities to control. So for example, you can select the frequency over some range, as done here, or power. And then you also select what to measure at each data point. So in this case, we're measuring some signal of the digitizer. And this interface provides synchronization between instruments and also make sure that you run your sequences in the right order. Once you have added your instruments and defined your step settings, you can click start, and then you will see in real time as data coming into your device. You see a nice visualization of both the data coming in as a line trace and also the 2D map here. Now, the last part of Labware is the log browser, which allows you to, after the measurement is done, go back and look at data. So it talks to a database where we have the database storage of all the experiments. This screen here shows what the log browser looks like. You have on the left a bunch of experiments that have been measured in the lab, and on the right you see a quick preview of what was taken, what measurement was taken. So it contains all the measurement settings as well as a quick image of what was measured. And if you want to look at things more detail, you can open up these log files and do more advanced image analysis like cross sections or various smoothing, rotations, or operations to the data. And it's very simple to export data to nice looking figures for presentations or for papers. This part shows the user interface part of Labber. There's also a corresponding API through Python, which we can use to control things through a programmatic interface. And I'm showing a quick sample here, which will show what it looks like if you want to run these things again from code. So I'm not going to go through the whole thing, but you essentially define what things you want to measure, and then you can make a for loop of things you want to step through and update various parameters, run measurements, get data back, and do data feeding. And this can be done in a pretty seamless way. We still utilize the strengths of Labber, which is the nice user interface and the data visualization, while still doing full control of things through this Python API. All right, so that part showed what Labber looks like as its base product. At this point, I will switch gears and move over to the more quantum-specific applications of the software. This slide here shows a typical quantum computing stack, where at the very top, you have the quantum algorithm that you want to implement. This could be any of your favorite quantum programming language, for example, Liquid, Cousin, Q, etc. I think this example I'm showing here is in Microsoft's language. The next step on this is where you compile this algorithm into quantum gate operations. So this is then compiled into various gates applied to the qubits. The next step under there is where you convert these kind of abstract quantum gates into specific control pulses that apply to the qubits you want to use. And the shape of these control pulses will depend strongly on what kind of qubits you have. So if you're doing, for example, transmon style qubits, it's going to be a mix of baseband and microwave pulses. If you're doing spin qubits, it's going to be also a mix of different kind of pulses, but it will be different for different types of qubits. Then the next step is to apply these control waveforms onto the physical hardware, which then is being sent down to the quantum devices at the very bottom of the stack. And our solution kind of lives in this space in between the abstract gates and the physical quantum hardware. So we take care of the generation of specific control waveforms and upload them to the classical hardware, which then again will apply these pulses and waveform onto the quantum devices at the bottom of the stack. So there are plenty of things that you need to do in this kind of middle layer of the stack to be able to run successful quantum experiments. Again, the first thing you want to do is to convert these abstract gates into qubit control pulses and implement these pulses on the classical hardware. But in addition, you want to do a bunch of things that are kind of more delicate or intricate. For example, to remove crosstalk between qubits that you need to first characterize. There's also quite frequently a lot of drift in qubit parameters. You need to have a way to frequently recalibrate and compensate for this drift. You also want to implement things like basic error correction protocols to mitigate dephasing in these systems. So this could be things like refocusing pulses or spin echoes to remove the effect of slow noise in your system. And finally, you want to be able to benchmark the performance of the qubits. So our solution also contains basic tools for doing benchmarking of quantum systems. And altogether, our solution kind of allows the clients to implement the intended quantum algorithm. And this slide here is going to show how we divide up the task between what was known as Labber, this kind of base level software, which does general purpose instrument control and automation. with these more quant-specific solutions that live on top of Labber. So again, the quantum part of Labber is doing the quantum-specific initial signals, so waveforms, and also the quantum-specific signal processing, which could be things like the modulation of readout tones to disharmonic qubit states, or things like generation of waveform using pulse primitives specific for qubit rotations. It also includes things like dynamical noise suppression using spin echoes or similar techniques to remove the effect of low frequency noise. It includes calibration and verification. So again, keeping track of drifting parameters over time, make sure you can compensate for them so that you don't suffer from low frequency noise in your system. And finally, it includes a scheduler for running, for example, if you want to run experiments every 24 hours, this could be things like calibration experiments that you want to run once a day to make sure your system is tuned up. Our current focus is to move some of these parts from software into hardware. So essentially, we want to put as much as possible of this signal processing and generation and noise suppression away from software onto custom hardware, for example, FPGA or custom electronics. This will allow experiments to be sped up and also to enable users to implement things like feedback or quantum error correction. And with this, I want to thank you for attention and happy to take questions.
Thanks a lot, Simon, for the presentation. So I think we have a lot of time for questions, and there is already a first one. So do you offer control flow operations in your framework?
That is not something we do in the framework we have currently. So that will be more when you want to run things, including conditionals. I should say this is pretty front edge of research today. There's very few systems that are having long enough coherence times and fast enough feedback systems with low enough latency to allow that. And Labber, as a software system, does not support the control flow or conditionals currently.
Okay, thanks a lot. And here's another question. So how is the connection between Labber and higher application layers? For example, do you offer any integration with tools such as Keysight, Zurich, and so on?
We do not offer direct integration to tools like Keysight or Zurich. You can certainly write it if you wanted to. It's essentially a converting the way you define pulses and control sequences and gates in Keysight or Zurich to the way we do it in Labber. But we don't have a direct like tool for doing it currently.
So this basically means the user will learn the particular interface that Labber has, and then they specify their quantum circuits in this interface.
Yeah, I would say there are a large number of ways to define these circuits, and we have our own way to do it. So it's kind of tied to how you do it with the hardware, and it's pretty straightforward to convert them. So yeah, it's not a fairly trivial task to convert these different ways to define the algorithms. Again, with this exception then for the latest version of Keysight has support for conditionals, which again something we do not support currently with Labber.
Then there's a question about licensing. Are you planning to open source or some open source Labber or Labber Quantum?
Yeah, a small part of Labber is open sourced, which is the drivers part. So the very base layer, the interface that talks to the various classical hardware is open sourced. We do not have a plan currently to open source anything else.
Okay, then there would be another question. So you say you allow clients to implement the intended quantum algorithms. So what about clients who are more interested in the research on a lower level, like for example, particular new control waveforms, for example? Is there enough flexibility to integrate such own waveforms into Labber?
Yeah, that would fall under what we call the open source part of Labber, so the kind of base layer where you do both instrument control, but also there are ways to create your own waveform generation drivers. So you would then essentially replace our standard way to create qubit control waveforms with your specific way to create waveforms. And that part, again, is living in this open source level of Labber. And as you said, it's been used to create very different kinds of waveforms and systems for many different kind of quantum applications.
Okay, thanks a lot for answering these questions. So if there's still one last question, there would be the chance to type it quickly in this Q&A function of Zoom. So otherwise, I should have maybe said it earlier. You're feel free to already type your questions also while the speakers are still talking, and then we can treat these questions afterwards in the question and answer session like now. So for the next speakers, you know already that you can type while the presentation is still ongoing. Okay, now it seems that there are no further spontaneous questions for this first talk. Then just thanks again, Simon, for the presentation and for the discussion.
Yep, thank you.
And then let's move on to the next speaker. So the second talk is by Adriaan Rol, who received his PhD from TU Delft, where he worked on control for superconducting qubit systems, and he also contributed to a predecessor of QTech's Quantum Inspire platform. And Adriaan is now Director of R&D at OrangeQS, and he will present Quantify, an open source data acquisition framework for quantum computing and solid state physics. So please, Adriaan.
Thank you very much for this introduction. And also thank you very much for Zurich Instrument for hosting me here in Zurich. So what I'll be talking about is Quantify. It's an open source data acquisition platform that we are developing together with QBooks, startup from Delft. And there's a few things I want to talk about. Of course, very much thanks also to Simon for introducing the problem a bit, because what we're doing is very much working on the same problem. And the first question I'm going to address is why would we develop an open source data acquisition platform? After that, I'll go into explaining what Quantify exactly is, what it does and what it does not do. And then I have two examples of how we're using Quantify in practice. I expect that I'll be able to get through the whole transpond story within the timeline. We also used it to run a variational quantum eigensolver for simulation of the hydrogen atom. But I'm not sure if we can get through that part of the presentation due to time constraints, and I would like to leave some time for questions. So the first part, why are we doing this? And it really starts with like zooming out a bit, because we're at the Quantum Industry Day. There's a big market for quantum computing that's emerging, but what we really need to do is we need to develop useful quantum computers. And if we look at that, we see that most of the large commercial players, think IBM, Google, but also what you see a lot, for example, what Fraunhofer was saying is really this focus on the applications in the HPC quantum computing. But in order to provide this useful application, we need to scale both the number as well as the performance of the qubits. And this is typically done through what we like to call the quantum device engineering cycle. And funnily enough, the most challenging part, or the most expensive, time-consuming part, is actually the characterization. And a lot of academic solutions, as Simon said, are not really suitable to really take that to the next level. And we need to develop a good software framework to work on that. Why not take some of the existing open source things? Well, this focus on applications and the end user is really reflected also in the state of most quantum software. So most of the open source framework, Qiskit was named before, but pretty much all of them, they focus very much on the space of the quantum algorithms. And this is essentially the level they look at. And it's very good. It's usually open source, well-maintained, pushing the envelope on what the state of the art is. So very impressive work. However, it's also very much focused top-down, meaning it's focused on this end-user application. And all the complexity that's actually in the experimental physics is completely hidden away. And that's really the layer where we're focusing on, this calibration and characterization problem. And that's what I'll be talking about. Now, what about Piked? Now, this audience might not be as familiar with Piked, but Piked is a typical example of the academic software. This is something that we developed in Delft several years ago, and it's pretty great. It has few concepts. There's a minimal user interface, meaning it's contrary to the Labor solution. It's a command line and code-based interface, which has some advantages if you want to go towards automation. It's really open source and has a very extensive library, so lots of experiments. With the exception of a few notable exceptions, like Labor QCodes, there's not really that much that's targeting this niche of experimental physics. So I really commend those organizers for creating this session on this subject and having a talk about it. But the problem with this academic software, why we can build on it, is basically that it's not documented. There's no continuity in maintenance, and there's typically this don't touch it, work kind of mentality. And so we really said we need to rebuild this from scratch. So Quantify has been designed to address these core challenges. The typical requirements that we had in mind are these lists. On one, we need to be flexible. That means that the framework should be able to deal with things that we did not think about when thinking about it. Also, it implies that the code should be modular, reusable. Another key requirement that really comes from the more recent years that we want to be able to automate experiments. And that's really also where we get this idea of going for a minimal GUI, but we need to include the experiment and analysis in the same framework so we really close this loop and have that barrier be a very small step also for the user. Easy to use goes without saying. We want minimal training, implies good documentation, minimum set of concepts. And the final one is also that we believe that this framework needs to be open source. The reason has to do with that you really need to be able to look at the source code to figure out why your experiment isn't working. There's lots of strange things that can happen in the lab. Also, a nice property of open source that avoids the vendor lock-in. That's something we encounter, that people they don't like to commit for this kind of deep infrastructure to one particular supplier for what they're doing. But also because it's open source, we can actually facilitate the standardization and collaboration. People can build on it and make more advanced solutions. So if we then look at what Quantify is, we separated this into two modules. We have Quantify-core, that's the core framework, and Quantify scheduler. And that's really a cool thing where we seamlessly combine this requirement to be able to do the quantum circuit level operations and the pulse level operations. I'll get back to that in a little bit. So the core concepts of Quantify-core are first the instrument parameters. Here we make use of the EQuS framework. This is an open source project developed by Microsoft and has a very extensive library of instrument drivers and allows us to not reinvent the wheel. And that's also part of why we're doing this open source. You don't want to do everything from scratch. If there's a good thing out there, you should be using it. The next part is the measurement control in combination with the settable and the gettables. And this is actually a very flexible framework that imposes a bit of standardization on how you're doing their experiments to ensure that all the data sets look the same. This helps when you write analysis code, but also to allow you to do very advanced things, like, for example, adaptive experiments. What you're seeing here is a minimization algorithm. This particular data set is from the live visualization tutorials, but this can, for example, is very commonly used when you're calibrating mixers or when running a variational algorithm. And finally, there's also the data storage and analysis. We're basing this on the X-array module, also writes the same HT5 data format that I just saw that Laura was using. It's essentially a way of storing a database with arrays with metadata like units, and has a lot of utilities built in. And then it also comes with an analysis framework. You see here an example of how we're fitting to a resonator. As I mentioned, we also put a lot of emphasis on documentation this time around, because that's really one of the limitations. How do you make sure people can actually use that? Here you see an example of the documentation user guide of Quantify-core. There's also quite a few tutorials. You can look this up online, so check it out. Where it gets really cool is when we start talking about sequencing or scheduling. And the thing is that if we're looking at this typical layered architecture with the quantum circuit on top for the quantum algorithms, and then going down into the pulse level and having this hard separation, what we're actually finding is that this paradigm is good for most quantum algorithms. Once you're starting to do variational algorithms where you have continuous gate sets, it doesn't fit too well, but with a few small modifications, you can still make it work. And then you see sort of parameterized gates. It doesn't fit neatly, but it kind of works. The big problem is, however, that it's completely unsuitable for characterization and calibration. And you might wonder why that is. So if you're thinking about the requirements, operations are typically pulses instead of quantum gates. So you need to think about what's actually the pulse. Can you put optimal control in there? Can I try new waveforms? Lots of things you want to be doing there, but also you just, even if you have a fixed pulse shape, you still want to be able to vary the parameters to calibrate them. There's precise timing control required. Typically, you want to be specified what nanosecond your operation starts. And you typically want to apply that to a certain location on your device because the abstracting of a qubit doesn't exist when you're just characterizing a resonator, for example. Now, you might still think you can separate the gate layer and the pulse layer, but the problem is that very often you need the power of the abstraction of these quantum circuits. And a good example here is the Chevron experiment. This is a very standard experiment in which you're trying to either determine how strongly two levels are coupled, or, for example, use it to very quickly understand how are your distortion corrections for your pulses working. And what you see here is we're having a quantum circuit. That's the easiest way to describe this, with real fixed operations, except for one that's a square pulse of which we're varying the duration and the amplitude. So this is a prime example of where you really want to be combining these two levels of abstraction. So how do we do that? So when we quantify, we use a very standard conventional layering structure. On the top, we have the quantum circuits, gates, measurements acting on qubits. Below that, the quantum device layer, we're applying pulses and acquisition protocols, how we interpret the signals to locations known as ports and frequencies specified by a certain clock. And this gets then compiled into instructions that act on the hardware. Now, the top level quantum circuit layer is completely device agnostic, and we can then compile this into instructions that are device specific. We do this by specifying a configuration file, selects a backend which system you want to compile for, and contains the calibrated pulse parameters. Similarly, if we have a configuration that specifies then how things are connected to the control hardware, what kind of attenuation is used, those kind of parameters, we can compile it into the control electronics. Also very important, for us it's very important that we're able to use control electronics of different manufacturers. So currently we have a backend for both for the EQuS hardware as well as for the Zurich Instruments hardware, both which are used in experiments. And we're also planning on extending this with different manufacturers. So what's the small modification we can make? How can we make this work for the seamlessly combining of the layers? Well, with the quantum circuit layer, the order of the operation matters. And we have gates and measurements. In the device layer, it's not the order, but the timing that matters. And there's pulse and acquisition protocol. So with the realization that gates and pulses, they're both different representations of the same operation, we can just add operations to our schedule. And also realizing that when you specify the timing, you're actually also specifying the order. So this allows us to simply add operations to a schedule with timing constraints. When they're specified at the quantum circuit layer, the compilation step can add the missing information. If they're specified at the pulse layer, we're able to compiling them down, and this allows us to really combine this. Now I'm seeing I'm going a bit slow, so I'm going to skip over this figure. You can read up on this in our documentation that we have online. And I'm going to skip a bit to the lab-specific experiment libraries. So one of the things we did is we made all of this work for the standard transmon calibrations. Here you have an example. So here you see on the one where we generate a schedule, you can see here, this is a schedule, we add these distinct operations, this time at the pulse level. We can specify the timing using timing constraints. These are very flexible. If you don't specify anything, they go back to the last operation, but you can also really specify timing in detail with respect to specific pulses. Then we say we want to vary the parameters. We can see here the way we pass these arguments to the schedule generating function we can in principle vary any parameter. And here we see that in the measurement control, you say, hey, I want to be varying these parameters over these values. We measure this in the impact projects, a project with different companies in Delft. We said, put all the things together, make a quantum computer. Here you see standard resonator power scans. One little detail that I always like is that we have these labels that are unit aware. It's super tiny, but it just makes your life so much easier that you don't have to worry about these things in the standard plotting facilities. As I mentioned, the next thing was we said combine all of this in this project, where we go from the standard spectroscopy experiments to the standard time domain experiments. Here you see a Rabi in 2 dimensions, mostly here because this way of visualizing it looks pretty, but to demonstrate we have coherent control. This was done in the impact project, where with a consortium of different companies said, hey, if we put all our components together, we actually have a fully functional quantum computer. And we can see here that we have all the standard things where we see here coherence, we see here a calibrated XY plot. But one thing that I'm also very excited about is sort of what we did after that, because we're not doing anything new here. This is not next level science, but we're rebuilding everything from scratch. And why we're doing this is, for example, to be able to do things like get our hardware abstractions right, and in this case, get an emulator in there. So the emulator